Hello calculus students. Today we will be starting section 4.4 and this is on concavity and the second derivative test. We're going to look into points of inflection, which are points where the concavity changes in the curve, where it might go from a happy face to a sad face. That change is called a point of inflection. First, look at your notes. It's just going to fold into a pamphlet. So have example 1 and 2 face up facing you. Fold the right flap in and then fold the left flap so that 4.4 concavity title is on top. So let's begin. Let's look at the graph here. You can see that we have tangents all along this piece of curve. Notice all the tangent lines are below the curve, or in other words, the graph lies above the tangent lines. When that happens, you can see that it makes a concave upward curve. Let's look at this graph. Now we can see it's concave down because it looks like a sad face. And notice all the tangent lines are above. So the graph is below the tangent lines. When the graph is below, it means it's concave downward. To find the intervals on when the graph is concave up and down, we want to know when the intervals of the first derivative is increasing or decreasing. Let's look at another piece of curve. Let's sketch a curve that goes up and down, up or down. I'm going to do a little piece of curve that goes both. So there's like a sad face and into a happy face. Now think about the slopes going around my curve. For instance, here's a tangent line. I would say the slope is maybe about 1/2. And then here, I get a slope of -1/2, let's say. If I draw a tangent here, the slope is -3, let's say. So compare my slopes. It went from 1/2, -1/2 to -3. The slopes are decreasing. So when I have a concave down piece of curve, the first derivative, or those slopes, are decreasing. If you were to do the same on the happy face section, that looks like -3, let's say. Here we have 0, and then we're going to increase to positive. So these are increasing. And when it increases, we have a concave up shape. So let's look at our test for concavity. Let's say we have a function where the second derivative exists. If the second derivative is greater than 0, meaning positive, then the graph is concave up, or a happy face. If the second derivative, this is second derivative, can't see that's the symbol, is less than 0 or negative on that interval, then the graph will be concave down. So how can we find concavity? Let's follow these basic steps. First, you'll now need to find the second derivative. Decide when the second derivative is equal to 0 and when it's undefined. Write the PPIs. PPI stands for possible points of inflection. So although right now they're called possible because we have to test to decide if they will become a point of inflection. Right now it's a possible point. What we need to then do is choose a test number in each interval. Use those possible points of inflections to break up your interval. Decide what the sign of the second derivative is. And then you can make your conclusion on concavity. So let's try an example. Let's find the concavity of the function given. First, we need to find the second derivative. Before we can find the second, let's find the first. I'm going to rewrite my original function by bringing the x squared plus 3 to the numerator. And now, complete power rule. -1 times 6. Copy down the function. Subtract 1 times the derivative of the inside. I'm going to clean this up and make it -12x over x squared plus 3 to the -2. Actually, since I have to find my second derivative, I'm going to leave it in the numerator and go ahead and find the second derivative before rewriting it with positive exponents. So I now introduce another variable, so I have to do a u times a v with a chain rule. So second derivative, u prime will be negative 12, copy down the v, plus copy down the u, v prime, I'll move the negative 2 to the front of its function, subtract 1, times it by the derivative of the inside, which will be 2x again. I'm just going to clean up a little bit. For instance, the negative 12x, the negative 2, and the 2x in the back, I'm going to multiply together and get negative 12 times 2 is 24 times 2, 48x squared, x squared plus 3, the negative 3 still. So now I have x squared plus 3 in both terms, and I'm going to factor that out. Factor the smaller power, which is negative 3. When I do that, the first term I'm left with negative 12, and then x squared plus 3 to a power of 1. And then I have 48x squared left over, and all of this will factor out. I am then going to clean up inside my brackets and bring x squared plus 3 to the negative 3 to the numerator. So my second derivative will finally look like 36x squared minus 36 all over x squared plus 3 cubed, equaling the numerator to 0 and equaling the denominator to 0 will give me our undefined. On the numerator side, or on the left, when it equals 0, I'm going to add 36 and then divide by 36, square root, I get plus or minus 1. On the right side here, I'm going to be square rooting a negative, which will be imaginary, so none. So my PPIs are 1 and negative 1. So I'm going to put those numbers on a number line so I can make my intervals, negative infinity to negative 1, negative 1 to 1, and 1 to infinity. We can then choose a test number in each interval, like negative 2, 0, and 2. You want to test this out into the second derivative. So plugging negative 2 into the numerator will give me a positive in the numerator. Look at the denominator. When I do negative 2 or any number, it's going to square, so it will always be positive. The denominator for this whole entire problem will always be positive. So I'm left with a positive. Plugging 0 in the numerator, I'll have a negative, and I already said the denominator will always be positive, so that'll give me a negative. And then plugging 2 in, I will get a positive. So here I will have concave up because it's positive, concave down because it's negative, and then concave up again here. Let's save example 2 to complete together as a class.